All right, so in these notes, we're going to talk about bond polarity and introduce the idea that bonds can be polar or they can be nonpolar. So we'll go through three examples. The first is a nonpolar covalent bond. The intermediate was a polar covalent bond. And then finally, over here, we're going to represent a 100% ionic bond. So the idea is that the more polar a bond gets, the less covalent it is, and the more ionic it gets. And so we talk about percent ionic character. And the classic ionic bond example is always sodium chloride. That would be considered 100% ionic in character, or very close to 100% ionic in character. And now that we have learned how to draw Lewis diagrams, we can represent a nonpolar covalent bond with a familiar one we've already drawn before. I'm going to draw a molecule of diatomic fluorine, and we know, of course, there are two shared electrons. We're going to talk about what makes this bond nonpolar is the fact that the electrons are shared evenly. And that has to do with electronegativity. In other words, fluorine is the most electronegative element on the table, and fluorine is just as electronegative as fluorine, which means these electrons will be shared evenly between those two atoms. So I'm going to draw an electron cloud represented as a pretty uniform shape, which doesn't have any polarity to it. It doesn't have a positive end or a negative end. There's not really a separation of charge density from one molecule, one side of the molecule to the other. But over here, to represent a polar covalent bond, I'm going to give the extreme example of hydrofluoric acid, where hydrogen, of course, only has one electron that it brings to the party, and it's busy in that bond over on the right. And so all of the electron density is concentrated over towards fluorine. This would be a very polar covalent bond because while there is sharing going on, it's not an even sharing. And of course, the last example I'm going to give is where there's no sharing going on at all. And we're going to represent that with sodium fluoride. There's the sodium cation. Here's the fluoride anion, which has already gained an electron, and the sodium has lost one. And there's no sharing going on at all. So let's summarize what's going on in terms of electron sharing. Here, electrons are shared evenly. Here, electrons are shared unevenly. And here, there is no electron sharing. Electrons have been transferred from the metal to the nonmetal in the case of an ionic bond. So this is what we're going to consider increasing ionic character. And the distinction between ionic and covalent ends up being a little bit less distinct in this way. It's not simply a matter of a bond is either ionic or it's covalent. There's many ways to define this, and one of them is by looking at the difference in electronegativity. So the last column that I want to add here has to do with those differences in electronegativities between two atoms. Now, electronegativity values are measured many different ways. The most common is to use the Pauling electronegativity scale, which ranks fluorine as an electronegativity of 4.0 and all the other elements less than that. And while we don't often need to get into the details of electronegativity values as numeric values, there are some guidelines that it might be helpful for us to know about. If the difference in electronegativity, so I'm going to write electronegativity delta for the difference in electronegativity between the two atoms involved, is less than 0.4, then we're talking about a nonpolar covalent bond. And of course, it makes sense that that's the case here, since the difference in electronegativity would be 0. What's 4 minus 4? That's 0. There's no difference in electronegativity between fluorine and fluorine. If the electronegativity delta, the difference in electronegativity, is somewhere between 0.4 and 1.7, we'd consider it to still be a covalent bond, but we consider it to be a polar covalent bond. And that's just the range where we say, yeah, it's not ionic, it's not greater than 1.7, and it's really polar, though it's not nonpolar. And of course, over here, if the electronegativity delta, or the difference in electronegativity, is greater than 1.7, then that's considered to be more ionic in character than covalent in character. So we go from sharing nicely to sharing but not very nicely to not sharing at all.